So this is another example that's going to connect back to what we did in introductory physics when we were looking at forces and finding acceleration, calculating deflections, motion for particles in when they experience forces. So you'll see this works in much the same way. So the idea is that we have a uniform electric field. So electric field is constant. Points to the right in this case is uniform. So it doesn't change its values. And we have an electron entering the field with an initial speed of v0, and it goes this distance in the y, h, and then it also deflects. So the first thing we want to know is which way does it deflect. So it's going to deflect away from the negative plates. So it's going to, this is the negative here, the negative plates that are set up are what generate this field. So we have positive plates on one side and negative on the other. And so this actually, instead of going straight, is going to start curving until it gets out, and then it's going to go straight again because there are no forces on it, right? But right in here, it experiences a force that's to the left because it's a negative charge. A positive force would experience, a positive charge would experience a force to the right. But in this case, we have a negative charge, so it goes the other direction. So it's going to do something like that. It's going to curve. And so in order to find that, figure out the motion and find out how far it deflects, because that's really what we want, is an expression of how much this deflects. We'll call this a delta x, right? And so in order to find that, we can say, well, if we look at what's going on in the x direction and what's going on in the y direction, we can again separate things into components and recognize that the sum of the forces in the y direction is equal to 0. There's no acceleration in the y direction because there's no electric field in the y direction. So because AY is 0, then that says from our kinematics equations all the way back to the beginning of physics 1 that y is equal to y0 plus v0 yt t plus 1/2 ayt squared, where ay is 0. If we say it starts at 0 and ends up at h, right? So we start there as 0 and h, then we have h is equal to whatever our initial speed was in the y direction, which would be v0 times t, which was fine, but that doesn't really tell us anything about x. But it's just to remind you that we have those equations and we can do something with them. In the x direction, however, we do have a force. We have a force that's equal to q times e. So that force must be equal to the mass times the acceleration. And the acceleration will be to the left. These will all be positive values as written here. We'll just know that that acceleration is to the left, and so the deflection is going to be to the left. And so that force is equal to q times whatever the electric field is. So the acceleration in the x direction is equal to q times e over the mass. So if it's an electron, we would put in the charge of an electron, q, and the mass of the electron, and then put in the electric field. And then because it's a constant electric field, that's why that's important for this problem, we can use our constant acceleration equations. Now, if the electric field is changing, we cannot use our constant acceleration equations. But here, we can just repeat the same equation, x equals x0 plus v0 in the x direction t plus 1/2 at squared in the x direction. So we can say we start, we can actually set up our axis here. We can say our initial x is 0. Our final x is this deflection, delta x. And we don't have any initial speed in the x direction, so that goes to 0. So this just becomes 1/2 ax t squared. And so we can substitute in whatever number that is, depending on the electric field. So we can substitute that in and say delta x is equal to 1/2 q e over m, and then the t squared is the time that it spends in between these plates, so that we could actually solve for over here. So the time that it spends depends on how fast it's initially entering this electric field region. So the time is equal to h over V naught, where h is this distance here, the height of this setup. And so we can put that in as our t squared, so that would be h over V naught squared. And so once we had all of these numbers, we could just find out what this deflection was. And this is a way that we use to actually steer charged particles, right? We set up these kinds of electric fields, we send them through, and then we can steer them very nicely with electric fields to send them where we want them to go. And this is the way we used to with those old cathode ray tube TVs. When you had a big TV set, we would steer them using this or magnetic means.